Okay, coming back to the very last topic in this section, the distance between a point and a line. Well, let's draw a picture to see what is this about. Well, so number one, we have this line, and this line again happens to be defined as a vector valued function in parametric form, and we're going to have this point right here that we're going to call Q. That point is not on the line, and in fact where we're going to find this distance from Q to that line, and well, we're going to do this by means of choosing any point on the line. Let's call this any point P on the line. Alright? And well, this will generate a right triangle here. Alright, so in this case we're going to use trigonometry to get that distance. And well, just recall that because this line is defined parametrically, that line is going in the direction of some vector. Alright, so this one has a direction vector of let's just call it V for now. Alright, again, parametric lines, the coefficients of the t's for each component, x, y, and z component. Those coefficients are the components of that vector that go in the direction of that line, because recall we don't have slope for a line in 3D really, but rather we have a sense of direction in this case, and that's given by this vector. All right, so we want to find this distance d. Okay, using trigonometry, this distance d, well, and that distance from this vector PQ is going to be well related by the sine function, because that'll be the distance d, which is the opposite over the hypotenuse, and the hypotenuse is the magnitude of that vector that we will define between P and Q. Right, so that's d over the magnitude of P and Q. Okay, and well, how about we solve for that distance d in this case? Well, that's going to give us the following: d equals the magnitude of PQ times sine theta. Well, I mean, in this case we're not going to be given the angle, and in fact we don't even care about the angle. In fact, we're going to use a definition from last time, one definition for the cross product. Remember how the dot product is of the vectors is the product of the magnitudes times the cosine of the angle, and that was the formula that we used to find the angle between two vectors, and today we use it to find the angle between two planes. Well, the other version, which involves the cross product, is again the product of those magnitudes for which we're finding the cross product between, but in this case times sine of the angle, not cosine. So this is the definition, that is the magnitude, or rather the cross product, not a magnitude, this is the cross product between P and Q, and that vector V. Okay, well, it's actually, yeah, that's a magnitude. That's equal to the magnitude of the product of the magnitudes times sine of the angle. All right, and well, how are we going to connect these two formulas? Well, okay, so isn't this, okay, let me rearrange this formula. Let me write this product the other way. Isn't it this the same? All right, so I'm going to substitute this PQ cross with V instead of, so I'm going to have the magnitude of that vector V, which this vector V is in the direction of the line that we want to find the distance from the point to that line, and that's simply D, and all we do is divide both sides by D, and that's the magnitude of that cross product over the magnitude of the direction vector of the line. All right. Well, for those of you who will eventually take discrete mathematics, or if you are if you are a math major, so in this derivation we're using logics. What's the logic that we're using here? So just pretty basic here. If A equals to B and B equals to C, that means A equals to C. All right. In a way, we're using that kind of logic here, which you will see more in depth when you get to discrete and real analysis courses, abstract algebra. All right. So let's find the distance between the point for -1, 2. Well, your PDF should be updated. My file is not. There's some missing comma here. And the line given by -1 plus 3t, comma 2t, comma 4 plus t. Okay. Picture. This is the line. All right. This is r of t. Okay. And this is the point Q, which is given. Q is a point that is not on the line. Q, which is 4, -1, 2. Okay. So we want to find that distance between that that point and the line. However, we don't have a point P that it's on the line, so we can define a vector as we did in the derivation, but we can find one. Which point? It doesn't matter. It doesn't matter. Could be, for example, could be this point right here, and we define the vector PQ. All right. So no need to write this. Let me just show you. It could be this point right here as well. PQ, all right? And then we get that distance using that formula. It doesn't matter if that's that point. It could even be a point that is so further away over here, all right? P and Q. But the thing is this distance from Q and the plane changing regardless of the point that we choose? No. No, so you can choose your favorite point on this line, preferably the easiest point. Well, what do I mean by the easiest point? The easiest point is when you plug in t equals to 0 on the vector valued function. All right. So P will be the point P, which will be the initial vector of that we're going to use. So that'll be, let me use it. For simplicity, when t equals to 0, of course you can plug in the value of t equals to 1, that's fine. Or t equals to 2, that's fine, but I mean that's going to lead to more calculations. Plugging in zeros typically reduces the amount of work, right? So that's going to be r of 0, that's -1, plus 3 times 0, isn't that 0? 2 times 0 is 0, and 4 plus 0 is 4. But again, you might argue that this is a vector, not a point. But again, recall that these outputs that we get on vector valued functions are points on the line in this case. So this is equivalent to having this point right here, which is -1, 0, and 4. So now we have information to define the vector PQ. And again, to define the vector PQ, terminal minus initial, Q minus P, the points, the values rather, 4 minus -1, isn't that 5? And -1 minus 0, -1, and 2 minus 4, -2. And what else do we have? So we need to find the cross product of this vector and another vector, the vector V. And that vector V will be the component of the coefficients of t on the linear function, on the vector valued function, 3, 2, and 1. All right. So let me just highlight this. This vector right here comes from the coefficients of t. All right. And this vector PQ came from finding the difference between those points. All right. Terminal minus initial. Okay, so to find the distance between the the point and the line, we need to find first of all, we need to find the cross product. PQ crossed with V. All right. And in this case, we need to change the notation, which we haven't used at all today, the IJK version. So IJK, and that's 5, -1, -2, 3, 2, 1. All right. So as discussed before, you will have the freedom of computing this determinant the way you feel more comfortable with, either by expansion, by minors, which is what we did at the beginning of that section, or the shortcut that I showed you of repeating the first two columns. All right, but in this case, well, I'll just give you the answer to this cross product for the sake of time, to save some time. That's going to be 3i minus 11j plus 13k. So what do we have? That cross product, but we need to find that magnitude of that cross product that we just found. So that's the square root of 3 squared plus -11 squared plus 13 squared. And combining this together, this should give us the square root of 299. Okay. What else do we need? We also need the magnitude of the vector V, the vector in the direction of the line for which we want to find that distance between the point and the line. So that's the square root of 3 squared plus 2 squared plus 1 squared. So that's a 9 plus 4, that's 13, that's 14, the square root of 14. And the distance between the point and the line is the magnitude of that cross product divided by the magnitude of V. And in this case, that's the square root of 299 over the square root of 14. Final answer.